Hi, welcome to Chemical Kinetics Overview Part 3, where we're going to talk about the change of concentration with time, in particular integrated reaction rates. So the integrated rate law. Up until this point, we've been talking about rate laws. And rate laws show a relationship between the reactant rate and the concentration of the reactants. But what if you wanted to know the concentration at a specific time? Well, that's what the integrated rate law does. It gives you the ability to determine the concentration of a reactant at any time throughout the process of the reaction. Okay, so if you remember correctly, our rate law R, if we're assuming first order with our reactants, is the rate constant times the concentration of A. And that is also equal to the, because it's the reactant, the negative of the change in concentration over the change in time. So that's what we have right here. So if we rearrange this and get all our A's on one side, you basically have your change in A over the concentration of A, and you bring your negative sign to the other side, times a negative K delta T. Okay, and then if we use a little bit of calculus, and I'm not going to go into how to do that, but in case you were curious, this is the integral that you have to integrate. So we're basically integrating this reaction to get our integrated rate law. And after you integrate it, you basically get this law right here. And if we rearrange it, this is what we always refer to. So for a first order reaction, the integrated rate law is the natural log, ln is the natural log of your concentration at any time, T, equals negative K times the time, plus the natural log of your initial concentration. Okay? So AT is your concentration at time T, and A0 is your initial concentration. And basically, this is in the form of y equals mx plus b. So if you plot the natural log of your concentration versus time, and you take the slope of that, you could get your K value. So let's go over that a little bit slower. So after we use calculus and we integrate, we end up with this. But nobody likes fractions. And when you take the natural log of two things divided by each other, it's basically, so say you have the natural log of A over B, that is basically equal to the natural log of A minus the natural log of B. So in this case, we have the natural log of our concentration at time T over the initial concentration. So you end up just subtracting those two. And that is equal to negative KT. And then you bring it over so we could have it in this format here. Okay? Therefore, if a reaction is first order and you plot the natural log of the concentration versus time, you should get a straight line with a negative slope, and that slope would be your K value. So here again, we have a first order reaction, and data was collected, and they're plotting, because these are gases, they're plotting the pressure versus time. Now notice this is not linear. Okay? So then they take the natural log of the pressures and they replot it. So notice this is linear. So if your plot of your log, in this case it's pressure, versus time, is linear, then that means your reaction is first order. So when you plot the log of your pressure as a function of time, you get a straight line. That is telling you that this reaction is first order. Besides using the rate law, we can find the rate constant from the plot of this by calculating the slope. Using this equation here, you calculate the slope, and we get that the slope is equal to negative k. So that means k is equal to 5.1 times 10 to the minus 5 inverse seconds. Inverse seconds is just 1 over seconds. So how do we use this? Okay, so it's telling us we have a first order reaction. That's very nice that they told us that. And basically we're decomposing N2O5. So we have N2O5 breaking down into NO2 plus O2. It's first order, and they're giving you the rate constant. So they're giving us K. In 1 over seconds. And they said, suppose we start with 0.025 moles. Now notice this is not a concentration, this is moles. But they tell us the volume. So we could get the concentration. And it's the concentration we're starting with. So that's our initial. So you put that little 0 there to show that that's your initial concentration. So it's just your moles divided by your liters. So you get that your initial concentration is 0.0125 molar. And they're saying the time is 5 minutes. Look at how tricky they are. What is this in? This is in seconds. So we need to convert this to seconds. Okay, and what are they asking for? How many moles of N2O5 will remain after 5 minutes? So we know it's first order. So we know we're going to have our natural log of our concentration at 5 minutes, or 300 seconds, is equal to negative k times our time plus the natural log of our initial concentration. So let's plug in our numbers so we don't know this. This is what we're trying to solve for. Negative k is 6.82 times 10 to the minus 3 times our time, which is 300 seconds, plus the natural log of our initial concentration. So when you do all that math, you're going to end up with the natural log of N2O5 at 300 seconds is equal to negative 6.428. But I don't want to know the natural log. I want to know the actual concentration of this. So what you do to get rid of the natural log is you do e raised to the natural log. So in your calculator, you should have a little e button. So you raise both sides to e. So e raised to the natural log of this, and e raised to the natural log of that. So e raised to the natural log of anything will just give you whatever is in parentheses, which is what we're looking for. It's like the anti-log of the natural log is equal to e raised to negative 6.428. And when you put that in your calculator, you're going to get 1.62 times 10 to the minus 3 molar. What is the problem asking for? How many moles? Did we find moles? No, we found molarity. But we know our volume is 2 liters. So just multiply by 2 here, and you get your moles is 0.00323 moles. Now what is the second part? How many minutes, so now we're trying to solve for time, will it take to drop our concentration to 0.01 moles? Again, we need to divide this by our liters, right? So now it's saying our concentration at time t, that we don't know what the time is equal to 0.01 moles divided by 2 liters, which is 0.005 molar. So now we just plug that in. Our K is still the same. But now we are solving for time. So we leave T in there. plus our initial concentration did not change. And when you solve all this, you're going to get time is 134 seconds, but they want to know minutes. So you divide this by 60, and you get 2.24 minutes. So there's also something called half-life. And half-life is the amount of time it takes for 1/2 of your reactant to be used up in a chemical reaction. So if that's the case, if you are at that time where you've used up half of the concentration, that means the concentration at that time, which is the half-life time, is equal to 1/2 your initial concentration. Okay, so we take our first order reaction equation, and for AT, we're going to plug in 1/2 our initial concentration because we're at our 1/2 time. So you do that. There's quite a bit of algebra. You could go and look at this on your own, but basically the equation for the half-life is 0.693 divided by K. Log of 2, which is what is shown here, is equal to 0.693. So that's where that number comes from. So this is handy because if you know K, then you can get your half-life time. Oh, and I want to point out that in first order reactions, your half-life time is not dependent on concentration. All right, what about second order reactions? So remember, in your second order reaction, when you looked at your rate equation, you had your concentration raised to the power 2. Now, we're keeping this simple, and we're assuming we only have one reactant, okay? And the change in that reactant is this. So when you set them equal together, and do a little bit of rearranging, this is the equation that you end up having to integrate. And here is the integral, if you want to look at that on your leisure. If you know calculus, you can do that. But if you don't worry, because here is the end result. So here is your integrated rate law for a second order reaction. So now, in this case, when will you get a linear plot? When you plot 1 over A versus time. And notice that this is a positive K, so your graph will look like that. So here's an example of a second order reaction, the decomposition of NO2. What graph will yield a straight line? So look what we plotted here. The natural log of the concentration versus time, and look, that is not linear. So that tells us it is not first order. But when we plot 1 over the concentration versus time, look at how linear that is. That tells us it's second order. So that's how you determine the order. You have to plot it and look at the graphs. Okay? So if a process is second order in A, a plot of 1 over A versus time will give you a straight line. And the slope of this line is equal to K. So let's just go through this a little bit slower. So you have the decomposition reaction and you have this data. Is this process first or second order? Well, you don't know yet, right? So the first step you want to do is take your natural log of your data and plot it. And ask yourself, is this a straight line? And the answer is no. So it is not first order. So then you convert your data to 1 over the concentration, and then you plot it, and you ask yourself, is this a straight line? And the answer is yes, this is a straight line. So therefore, these 3 dots mean therefore, this is a second order reaction. And the slope of this line will give you K. So what is the half-life of a second order reaction? Well, I'm just going to highlight the equation to this. You could go through the math in your free time if you want. Remember, the concentration at time t is equal to 1/2 the initial concentration at your half-life. When you plug that all into your integrated rate law, you're going to get the half-life is equal to 1/k times the initial concentration. So the half-life here is concentration dependent for second order. Remember, it was not for first order. The last order we're going to talk about is zero order. Zero order means that your reaction is independent of the concentration of the reactant. And remember, your rate equation is just equal to K. And when you integrate this, you get this is your integrated rate law. So in this case, what are you going to plot? You're going to plot the concentration of A versus time. And you should get a straight line like that. And the slope of this line is negative K. So let's do an example here. So we have iodine dissociating into iodine atoms at 625 Kelvin with a first order reaction constant. This is K. What is the half-life? So we want to know T1/2 for this reaction. So the T1/2 equation for first order is 0.693 divided by K, and they gave us K. So we just plug in the value for K. And you get 2.56 seconds is the half-life time. Okay? So that was part one. Part two says if you start with 0.05 molar of I2, and this is your initial concentration, how much will remain? So we want to know what's going to be left at 5.12 seconds. So our time is 5.12 seconds. Okay, so we have to remember our first law rate equation. So it'll be equal to the natural log of our concentration at 5.12 seconds is equal to negative K times our time equals the plus the natural log of our initial concentration. So let's plug in our numbers. We don't know this number, so we're just going to keep this. This is what we're solving for, right? K is the same. Our time is 5.12 seconds plus the natural log of our initial concentration, which they gave us. Okay, when we do all this, we're going to get the natural log of I2 is equal to negative 4.38, but I don't want to know the natural log of it. I want to know it. So I have to do the antilog, or raise e raised to the natural log of I2 equals e raised to negative 4.38. So I get the concentration of I2 at 5.12 seconds is equal to 0.0125 molar. So it's tedious, but it's not so bad as long as you step through it. So I put this table together to kind of summarize, because I felt when I was going through this, I was getting confused what equations were what. So this will be a good reference for you to look back as you're solving problems. So this is your order, 0, 1, or 2. This is your rate law, right? If it's zero order, it's not dependent on the concentration at all. If it's first order, it's dependent on the concentration raised to 1. And if it's second order, it's K times the concentration raised to the order 2. Here's the calculus. You don't need to know this, but if you're interested, it is there for you. After you integrate it, these are your rate laws for each of your reaction orders. And here are your half-life equations. Okay? And here are the graphs that you would need to get a linear line to show that it is that reaction order. So for zero reaction order, when you plot concentration versus time, you should get a straight line, and the slope is negative K, and that tells you it's zero order. if you're plotting the natural log of concentration versus time, and you get a straight line, that tells you it's first order, and the slope is negative k. If you're plotting 1 over the concentration versus time, and you get a straight line, that tells you it's second order, and the slope is k. This is a positive slope. And I found this on the internet, and I thought this was a great overall summary. Please refer back to this. It basically talks about everything. It even shows you for each order, 0, 1, and 2, how your concentration versus time should look. It's only linear for 0, right? And then these are the same graphs. I just copied them and put them on the previous table. Okay, here are your rate laws, and here are your half-life, and here are your units of K. So I would refer back to this quite often so that you get to learn these equations. I would learn these equations, and I would learn these. And that is the end of part 3.